Okay, please go ahead, Marco.
Okay, so thank you very much. I would like to start by thanking the organizers for inviting me to contribute to this very nice trimester program in Bonn. I would also like to thank Jonathan Kujawa for the lectures he gave last week, and also in general for developing a theory which plays such an important role in everything I'm going to tell you this week. So the title for my talk, yes, is written here, and this will be based on a series of joint works with a few people. So with Azat Gainuddinov, Nathan Gear, Bertrand Patureau, and Ingo Runkel, all of whom have been mentioned last week. So I hope the subject will fit in nicely with the program. And I would like to start from maybe the first term in my title, which is TQFT. So TQFTs have a physical origin, but they have since evolved into a purely mathematical concept. So TQFT is an acronym for Topological Quantum Field Theory. And by paraphrasing a famous axiomatization due to Atiyah, which dates back to the end of the 80s, a TQFT can be formally defined as a symmetric monoidal functor from a category of n+1 cobordisms to the category of vector spaces. Now, the idea behind this definition, which is rather abstract, is, well, essentially the following. So a TQFT associates with every closed n-dimensional manifold vector space, and this is usually called the state space of the manifold. And it associates with every n+1 dimensional manifold whose boundary is parametrized and partitioned into incoming boundary and outgoing boundary. All of this is called an n+1 cobordism. Well, a TQFT associates with every n+1 cobordism a linear map from the state space of the incoming boundary to the state space of the outgoing boundary, like represented in this schematic picture here. And furthermore, a TQFT does this while also translating the topological operation of gluing, which defines the composition on a category of cobordisms, into the algebraic operation of composition of linear maps. And similarly, translating the topological operation of disjoint union, which induces a symmetric monodal structure on a category of cobordisms, to the tensor product of vector spaces, essentially. Now, one remark I would like to make about this definition is that I'm using here an indefinite article. So I'm in fact talking about a category of cobordisms instead of the category of cobordisms. And this is essentially because cobordisms are usually allowed to carry additional structure or maybe to be subject to certain restrictions, which may depend on the particular construction we might be considering. And it is customary to refer to all the resulting notions of functors as TQFTs. So we gather them all under this kind of umbrella term. Right. Now, if this is the first time you see such a definition, you might wonder, why should we care about such an abstract notion about TQFTs? So let me try to give some motivation. So first of all, a TQFT produces topological invariants of closed n+1 dimensional manifolds, which are usually called quantum invariants, and which enjoy good so-called locality properties, meaning that these invariants can be computed by cut and paste methods. So for instance, if you consider an n+1 dimensional closed manifold, like the one represented in this picture, then a TQFT will associate to it a linear endomorphism of the state space of the empty n-dimensional manifold. Now, since the empty n-dimensional manifold is the tensor unit for disjoint union, with respect to disjoint union, it has to be sent by a monoidal functor to the tensor unit for vector spaces, which is just the base field. So this is essentially a linear endomorphism of the base field. This is essentially a scalar attached to this n+1 manifold. And to compute the scalar, what you can do is you can first cut your closed n+1 manifold along codimension 1 submanifolds. And then you can compose the linear maps associated with this decomposition into cobordisms. And this is a very nice feature of quantum invariants coming from TQFTs. Now, a second motivation for caring about TQFTs is that, in fact, they have an extremely rich structure which allows for deep applications. For instance, every TQFT induces a family of representations for mapping class groups of closed n-dimensional manifolds. And since representations of mapping class groups are in general very hard to construct and very interesting to study, this makes TQFTs a very interesting tool. And so a sketch for the definition of these representations, I will be more precise later on, but for the moment, just a sketch. So a mapping class group of a manifold sigma is the group of isotopy classes of self-diffeomorphisms of this manifold. And so to a diffeomorphism F, we can associate a linear endomorphism of the state space of the manifold sigma. And this endomorphism is roughly defined by considering the cylinder over sigma, by parametrizing its outgoing boundary using the identity, and parametrizing the incoming boundary using the diffeomorphism F. This is a cobordism called the mapping cylinder of F. And now the TQFT gives a linear endomorphism of the state space of sigma. And this defines, in fact, a representation for the mapping class group. And this is a very interesting construction. So from now on, I will always assume n to be equal to 2. The only reason I gave the definition with the general n was to be able to draw these pictures for n equal 1. But from now on, objects will be surfaces in categories of cobordisms, and cobordisms will have dimension 3. This is the case that will be of interest. So now to construct TQFTs, there are several recipes. I will mainly focus on one kind of recipes for this week. So I will give a very partial account of the history on this topic. This is only because I would like to give some details, and talking about all the possible construction takes too much, takes too long. But the first construction I would like to mention is very famous, is due to Turaev. And it first appeared in his 1994 book, I have. And in fact, this construction builds on a previous construction on some groundbreaking work by Reshetikhin and Turaev, which dealt with less general settings, so a setting associated with the representation theory of certain Hopf algebras. And this in turn was inspired by some seminal work of Witten, who first found deep connections between certain mysterious topological invariants. And so he found an interpretation in terms of quantum field theory. He used some non-rigorous tools from the point of view of mathematics, such as Feynman's path integral. The insight provided by his work is huge. And this is just to say that there is a whole history I'm not telling you about behind this construction. You can check it in, there is some bibliography at the end of these slides. So if you want, you can check them. But anyway, for what I will tell you this week, Turaev introduces a certain notion of an algebraic structure called a modular fusion category. I will denote it with C bar. Now, I should point out the original terminology used by Turaev is simply that of modular categories. In fact, I am adding fusion here to the name just because, unfortunately, there will be a concurring definition for modular categories that will be relevant this week. And the second definition is more general. So to distinguish the two notions, I'm adding fusion here. I hope this is not too disrespectful with respect to the terminology, the original terminology of Turaev. This is a very famous notion, but just there are some terminology issues here, just to be clear about this. So from a modular fusion category, Turaev constructs a 2+1 TQFT, so a three-dimensional TQFT. I will denote it V sub C. And this TQFT carries with it several things. Well, as I said before, a topological invariant of closed-through manifolds. This is the famous Reshetikhin and Turaev invariant, and I will denote it RT sub C. And also a family of projective representations of mapping class groups of closed surfaces. Now, the reason why these representations are only projective and not linear representations has to do with the particular structure we need to equip coordinates with in order to make this construction. I will give more details later on. We could obtain linear representations, but then we would need to pass to a central extension of mapping class groups, a very small one, but anyway. So I will give more details later on. But what's important right now is that the main family of examples of modular fusion categories in the sense of Turaev are provided by semi-simple quotients of categories of finite dimensional representations of so-called small quantum groups. There is one, well, actually there is a family for every simple Lie algebra G. And the quotient is taken with respect to negligible morphisms. So this was something that was discussed also last week. And so if you take C to be the category of finite dimensional representations for this finite dimensional Hopf algebra called the small quantum group, and you take Q to be a root of unity, so this is the case that's relevant for this theory, then you can consider the quotient with respect to negligible morphisms, and this will be a modular category in the sense of Turaev. Now, once you pitch this construction this way, a natural question is, well, can we avoid this quotient operation? In fact, this quotient operation sacrifices a lot of algebraic information because these categories of representations before the quotient have a lot of non-semisimple phenomena. And so this is a natural question to ask. And this question was asked very early on. So there is an almost contemporary construction which is due to Lyubashenko. There is also some history behind this construction. In fact, it was preceded by very important work of Hennings, even though this suggests this work came later, but actually it was just published later. This dates back to the beginning of the 90s. And Hennings' work was concerned with the Hopf algebras again. But then Lyubashenko's work was furthered in a book in collaboration with Curler sometimes later. Anyway, for what interests me right now is that Lyubashenko introduces another notion of modular category. In fact, Turaev's notion was semi-simple by definition, and this notion of modular category relaxes the semi-simplicity assumption. It is still some kind of ribbon category, like in Turaev's approach, but just a little more general. And Lyubashenko uses a modular category to construct, first of all, an invariant of closed through manifolds. I denote this with L sub C for Lyubashenko, and also a family of projective representations of mapping class groups of closed surfaces. So these are all the nice byproducts of TQFT. Well, the main nice byproducts. And the main family of examples of modular categories in the sense of Lyubashenko is now provided by, well, not semi-simple, categories of finite dimensional representations of small quantum groups without quotienting negligible morphisms. So this is very, yes, sure.
So when you go back to the previous slide, I was surprised that you would take the small quantum group instead of Lustig's quantum group. But is this because you want later a finite dimensional Hopf algebra, or is there another reason? Okay. Mm-hmm.
Right. This is exactly the reason. So we want to work with finite dimensional Hopf algebras in this setting. There exist constructions which deal with infinite dimensional Hopf algebras, which are also very interesting. The theory you get in that case, so I'm not discussing it this week, unfortunately, but it's very interesting, has different phenomena that occur. So you have gradings you need to put on these categories, and then you have to equip manifolds and cobordisms with cohomology classes, and then you get graded TQFTs. It's kind of a different story, but yes.
Okay, thanks.
Okay, and right. So in this case, we can consider the original category of representation of finite dimensional representations for the small quantum group. This is a non-semi-simple category, and so now the natural questions are: first, does this construction carry, in fact, more topological information than the previous one? And second, well, since we have nice byproducts of TQFTs, can we also get TQFTs? And in fact, there are some problems that emerged early on with this kind of construction. The first one was observed first by Otsuki in a specific case, and then in general by Curler. And the problem is this one. So when C is a non-semi-simple category, and M is a closed three manifold whose first Betti number is strictly positive, so its first homology has a positive rank, then the Lyubashenko invariant associated with M vanishes, is 0. And this, unfortunately, it's a deep obstruction for the definition, for the construction of TQFT extensions. In fact, by some general properties of TQFTs, which have to do with symmetric monoidality, if you were to have a TQFT V sub C extending the Lyubashenko invariant, or indeed extending any invariant, then you would be able to compute the dimension of the state space of a surface as the invariant of the surface times S1. And this is a manifold which has first Betti number, which is strictly positive. So this is 0 for the Lyubashenko invariant associated with a non-semi-simple category. So in fact, this would mean the TQFT would have to be constantly 0. So this means, in fact, that the TQFT doesn't exist. So this was a first kind of negative result. And the second one came a little bit later, and it's a result by Chen, Kupum, and Srinivasan. And they showed that in the main family of examples, so when you consider C to be the category of finite dimensional representations for the small quantum group of SL2, this is the simplest small quantum group you can consider. And when you take C bar to be the quotient by negligible morphisms, so this is modular in the sense of Turaev, then Lyubashenko's invariant of M can be written as the product of H1 of M with the Reshetikhin and Turaev invariant of M. And here, H1 of M is just the order of the first homology. So it's exactly the order when the first homology is finite, and it's zero otherwise. So in fact, this seems to indicate that Lukashenko's construction might not give more information after all. It might give less, it seems like, at least in this example. So I think these kind of negative results, we could say, were one of the reasons why these deep constructions by Lukashenko and Curler with Lukashenko were underestimated for a long time, I feel. In fact, these are very deep constructions, and maybe there was something missing from this approach, this early approach to non-semisimple quantum topology. And what was missing is precisely the theory of modified traces. So one way of explaining why Lukashenko's invariant vanish a lot is that, as we saw also last week, when C is a non-semisimple category, well, a ribbon category, but if C is modular, is ribbon. So then there is a natural operation on this category that is actually pervasive in all quantum topological constructions. You do this all the time. And this is the categorical trace. And this operation becomes highly degenerate in the non-semisimple case. So for instance, if you consider any projective object P in the category C and any endomorphism of PF, then its categorical trace will vanish when C is non-semisimple. So in fact, once the theory of modified traces has been developed, it's kind of natural to say, well, let's replace the highly degenerate categorical trace with a non-degenerate modified trace. For instance, one defined on the ideal of projective objects. And this idea is not something that...
Marco,
yes?
Is this a good place for a small break? This cliffhanger?
If I can go one slide more, then it will be a perfect place for me.
Perfect. Good.
So I just wanted to say here that this is not a new idea. This idea of renormalization has been pioneered first by Costantino Guérin-Paturo in the kind of infinite dimensional setting I was mentioning earlier in 2012. So this is for unrolled quantum groups, more or less. Then it was used by Murakami without ever mentioning modified traces. In fact, this was done kind of independently of the theory of modified traces, but it was later extended and translated into the language of modified traces by Belyakova, Blanchet, and Gear. This was all in the context of the restricted quantum group of SL2. This was extended to TQFTs for general factorizable Hopf algebras by myself, Guérin-Paturo. This is just to say that the story I'm telling you this week is not the first time modified traces were successfully used for this purpose. But in our case, if we start from the Lukashenko invariant, then renormalization produces a renormalized invariant I will call L prime of C. And now this is a slide where I would like to stop. So I would like to first give you the main result I would like to explain this week, which can be stated as follows. So we will consider a modular category C over an algebraically closed field K. And this is a notion I will properly define later on. Then we consider a special category of cobordisms. This will be denoted cob with a check and subscript C. This is the so-called category of admissible decorated cobordisms. And there is a crucial admissibility condition here that has to do with the fact that traces in general are defined on proper ideals and not on the whole category. So we will want to compute traces in this process, and we will need some assumption in order to do this. And the theorem is the following. So there exists a 2+1 TQFT denoted V sub C, defined on the category of admissible decorated cobordisms. This extends both the renormalized invariant of Lubashenko and the projective representations in their original version as defined by Lubashenko. So this kind of answers completes the answer to the question I raised before. First of all, can we extend Lubashenko's constructions to TQFTs? Well, the invariant we cannot, but the representations, yes, we can. And there is a second point. There was the question about the topological content. I will try to explain why, very roughly speaking, the topological information carried by this TQFT is not contained in the one carried by the semi-simple version of the TQFT. So there is, in fact, much more. These representations have quite different properties, and these properties can be established using the TQFT. They weren't observed before. So this is what I plan to tell you after the break and for the rest of the week. I will stop here.
Great, thanks. Are there any questions at this point?
I would maybe have a question.
Yes.
So this type of TFT that you're considering here, if you consider all the TFTs that you define like this with this modified cobordism category, which is different from the one that one usually uses, can you classify these kind of TFTs possibly in terms of modular categories?
This is a very nice question, and I don't know the answer. So there are some classification results of TQFTs so I know one by a few people. It's 4 people. It's Bartlett, Schomer-Priest, Vickery, and Douglas, I think, if I remember correctly.
That is the classification that I'm familiar with, but your cobordism category
is different. It's different.
Right. It's not rigid,
right.
When the category is non-semi-simple.
Right.
So
right. Exactly.
None of the things that they are doing in their classification would go through with this. So, but still, I mean, you could ask whether, for instance, these type of TFTs that you're considering, whether they are classified by, say, non-semi-simple modular category.
Right. So this is, in fact, I don't know the actual, so I don't know of classification results. I think I recall hearing a talk by Schomer-Priest who explained that I'm not sure if there were classification results, but that essentially what we're doing to this cobordism category is we are removing certain morphisms from it. This is what we will be doing. And I think I recall that removing morphisms allowed for non-semi-simplicity also from the point of view of the classification results of these 4 people. I cannot tell you a precise result, but these classifications results I know dealt with extended TQFTs. So in fact, you have a notion of, you have some sort of 2-categorical version of this notion of TQFT, and there you start from a 2-category of cobordisms, and dimension 3 means that objects will be circles, will have dimension 1, and to a circle you will associate a linear category. And this classification result, I think you're probably familiar with it, but associates a linear category to the circle, and they prove that this linear category has to be a monoidal modular category in the sense of Turaev, if you start from the whole cobordism 2 category. And I guess by removing certain morphisms, you might be able to reach to get non-semi-simple image. In fact, there is a construction that does this. in the other setting, the one I was mentioning before, the infinite dimensional Hopf algebra setting, more or less, there is a kind of alternative non-semisimple theory using relative modular categories instead of modular categories. This is another notion. And I have a paper explaining how to construct, starting from that, an extended TQFT whose image of the circle is kind of, well, can be expressed in terms of this relative modular category, but this is not a classification result. So maybe I should stop here with the answer because I don't know.
Yeah, thanks for your answer.
Other questions? Well, I have a more naive question. So suppose I have a 3-manifold invariant and I would like to extend it to a 3-dimensional or 2+1 dimensional TQFT, but it doesn't quite work. How should I decide whether I should try to change the source cobordism category or whether I should try to change the target category?
Well, sometimes you have to do both. So for instance, in so this construction I was mentioning, you start with an invariant that is not so this admissibility condition here roughly means that you will be able to define your invariant for every 3 manifold, but these manifolds will be decorated and not all decorations will be admissible, will be good. So you will need some condition on the decoration in order to be able to define the invariant. This is kind of a necessary condition if you want to define this invariant. So there is kind of no question that we will have to work with a category of cobordisms that's missing certain morphisms. But in the other construction, what happens is that you first attempt using a universal construction to construct a functor. This will not be monoidal, and you have to pass to kind of upgrade the construction and replace the target category with a category of graded vector spaces, or, well, in the case of extended TQFTs, of graded linear categories, and then you will get a monoidal functor. So sometimes you need to do both.
Great, thank you. Is there a quick question before we continue? That doesn't seem to be a case. Okay, good. You ready to continue?
Yes. Okay. So now for my plan for the rest of for the rest of the week will be to first present the algebraic setup I'm going to use for this topological construction. This will take, I think, the rest of today and maybe the first part of tomorrow's talk. So there is some setup I need to introduce. Then tomorrow, I hope I will be able to tell you about how to use the algebraic setup in order to construct topological invariants of closed 3 manifolds, these renormalized Lubashenko invariants featuring modified traces. Then maybe Thursday, I will tell you how to extend these invariants to TQFTs. And I will also tell you what are the properties of the mapping class group representations induced by these TQFTs and why they show some phenomena which wasn't present in the semi-simple theory. And in fact, they have very interesting properties that are new in quantum topology. Okay, at least that are new to this new wave of non-semi-simple construction using modified traces. So they are also shared by other works I mentioned earlier, but recent ones. So anyway, I will start with the algebraic setup. So first of all, I'll fix a few conventions. I will use an algebraically closed field K for the whole week. The requirement that K is algebraically closed, can be relaxed. It's useful to work. It's simple to work in an algebraically closed setting. So I will make this assumption for this week. But the field K can have positive characteristics. So no restriction there. And then I will denote with the letter C a linear category over K. Everything linear will be linear over K. And the linear category is just a category whose sets of morphisms carry structures of vector spaces, which make the composition into a bilinear map. Right, so the first term I introduce is finiteness. So we say a linear category C is finite if it is equivalent to the category of finite dimensional representations for some finite dimensional algebra A. Now this is a rather implicit definition because the algebra A is not attached to C in any way. There exists a more explicit and equivalent definition of what it means to be finite. It was mentioned, I think, last week. So you can say this in terms of morphism spaces have finite dimension, and there being a finite number of isomorphism classes of simple objects, conditions like these. But I will use the cheap definition because it's quicker. So we also say a category C is ribbon if it comes equipped with several pieces of structure. We also saw this last week. So first thing is a tensor product. I will denote it with a standard notation, and it's a functor from C times C to C itself. Then it has to be equipped with a tensor unit, which is just an object of C. It has to be a rigid category, meaning that and in fact a pivotal category. So every object has to have a dual, and it has to come equipped with duality morphisms. So we will have left duality morphisms. I will represent them with a leftward arrow. And so for instance, the evaluation is a morphism from X dual tensor X to 1. The co-evaluation goes the other way. And we have right versions of these morphisms, right evaluation and right co-evaluation. 4 morphisms in total for every object of the category. It's not finished, so we also need a braiding, and the braiding is a kind of a natural family of isomorphisms in the category that are denoted C, X, Y. They go from X tensor Y to Y tensor X for every pair of objects X and Y. There is also twist morphism, which is a natural family of isomorphisms, one for every object of the category. They are denoted theta X. And all these pieces of structure are subject to several axioms. You can find a detailed version of these axioms, for instance, in the same reference that was given last week. So this book by Ettinghoff and other 3 people, so EGNO. It's a very nice book. But instead of giving you the details right now about all these axioms, let me give you maybe a topological way of understanding these axioms. So in fact, this was also discussed last week. We have a graphical calculus for morphisms of a ribbon category, right? And I will tell you about my conventions. So I will denote with an upward oriented vertical strand labeled by X the identity of the object X. I will read the morphisms from bottom to top, so this will be an endomorphism of X. I will denote with a downward oriented strand the identity of X dual. Then the evaluation, so the left evaluation will be a cap oriented towards the left. The left co-evaluation will be a cup oriented towards the left. Right versions are obtained from left versions by reversing the orientation. A braiding is represented by a crossing in our diagram. So this is an endomorphism from X tensor Y to Y tensor X. And a twist morphism is represented just by a small kink, so by a curl on our strand. And and there is also actually, so it's not here on the slide, but there might be more general morphisms in our category C that are not obtained by these building blocks. And for those, you just use the coupon notation. So you draw a small box, you label it by the morphism you want to represent, and this box is called a coupon. So and it will have strands going in and going out from the bottom and top boundaries. Right, so the composition in this for this diagrammatic calculus is given by just stacking vertically diagrams one on top of the other. Tensor product is given by horizontal juxtaposition. And the axioms now can be understood as invariants of this graphical calculus under isotopy and framed Reidemeister moves. So for instance, isotopy will give you the fact that these duality morphisms satisfy zigzag equations. I don't know, framed Reidemeister moves will tell you that the braiding is invertible, it is natural, that the twist is invertible, stuff like this. Okay, this is the idea for ribbon categories. And now an object of a ribbon category is said to be transparent if its double braiding with anyone in the category is trivial. So this is kind of the graphical representation for this equation. So if for every y in the category C, the double braiding with y is just the same as the identity of x tensor y, then you say x is transparent. And now we have the last piece of terminology here. We say the category C is factorizable if all of its transparent objects are isomorphic to direct sums of copies of the tensor unit. So this means that there are no non-trivial transparent objects. This is some kind of non-degeneracy condition for the braiding of this ribbon category. And now the definition is the following: modular category. So a category is modular if it is finite, factorizable, and ribbon, right? So one remark is that this is not actually the definition Lyubashenko came up with. Lyubashenko gave a different definition. This is equivalent, and it can be seen to be equivalent. So this is a deep result by Shimizu. It's in the bibliography. He in fact showed that there are, well, he considered several non-degeneracy conditions for braidings of a ribbon category, and he showed that 4 of them, the 4 he considered, are in fact all equivalent. One is Lyubashenko's. Another one is this very simple one, very cheap one. This is why I'm using this. And there are 2 other ones. So this is a very nice paper. Anyway, so now if C is modular and also semi-simple, then C is modular in the sense of Turaev. So in fact, Turaev's notion of modularity is this one of Lyubashenko plus semi-simplicity, okay? Even though also the definition of Turaev is not actually this one, but it's equivalent. And from now on, C will always be a modular category to me. Okay, in these slides, C will always be a modular category. Now, let me tell you a little bit about the main family of examples you should keep in mind, so that should thing become too abstract, you have some kind of concrete example in mind. To define them, we fix a root of unity. We fix Q to be equal to e to the 2 pi I over R, and we take R to be an odd integer, at least 3, okay? And now this is a definition of Lustig. We define U Q bar of SL2 to be the complex algebra. So as a complex algebra, this is defined by generators E, F, and K, and relations written here. So in fact, E and F to the power R are both equal to 0. So they are nilpotent of order R. K is invertible of order R. And now conjugating E by K gives you Q to the power 2 times E. Conjugating F by K gives you Q to the power minus 2 times F. And the commutators of E and F are given by K minus K inverse over Q minus Q inverse. This is some kind of quite famous algebra. In fact, it can be turned into a Hopf algebra by defining a coproduct, a co-unit, and an antipode like this. Instead of reading out all the definition, let me just tell you that if you now consider the category of finite dimensional representations for this algebra, this can be equipped with a tensor product induced by the coproduct on UQ bar. It can be induced with it admits a tensor unit, which is determined by the co-unit of UQ bar, and the antipode can be used to define a duality for these representations. So this is a pivotal category, in fact, just because of the Hopf algebra structure on UQ bar SL2. And now we can even define a ribbon structure. To do this, I will just introduce this very standard notation. So if A is a natural number, I denote by a curly bracket of A the quantity Q power A minus Q power minus A. Then the ratio of curly bracket A over curly bracket 1 is the quantum integer A. And the product of quantum integers between 1 and A is called it's the quantum factorial of A. Now, it's an early definition of Lustig. You can find it in its book, that this element here of the tensor square of UQ bar SL2 is an R matrix. So this is a special element of the tensor square of UQ SL2. There is a ribbon element that's a central element of UQ bar SL2 that's given by this other formula. Instead of giving deep comments about these formulas, I'm just putting them here because so that you can see that we have very explicit formulas. So everything is very explicit in this example. And now the R matrix can be used to define a braiding on the category C. The ribbon element can be used to define a twist on the category C. And now with this ribbon structure, C is a modular category. So this is a factorizable ribbon structure. And this is kind of the main example you can keep in mind for the rest of the talk. Right. Now the second ingredient I need, the second algebraic ingredient, is given by coends. Instead of introducing them in great generality, I will introduce them just for the very specific setting I need them for. So instead of giving them for arbitrary functors, I will fix this particular functor. This is sometimes called the inner morphism functor, I think. So this is a functor from the opposite category of C times C to C itself. It sends a pair of objects X and Y to X dual tensor Y. And now I need to tell you what a dinatural transformation of source H is. This is a kind of a classic notion in category theory, but it might be not so popular. So let me recall the definition. A dinatural transformation of source H is essentially an object of the category C equipped with a family of structure morphisms. I will denote them dx. And these structure morphisms have source, the functor H computed on the pair XX, and they have target the object D. And the fact that this family is dinatural means this condition. So precomposing with F on the left is equal to precomposing with F dual on the right, provided you consider this dinatural family of morphisms with the right object every time. So now the definition is that a coend of the functor H is the universal dinatural transformation of source H. So essentially, this is an object of the category C. I will denote it with a curly L for Lubashenko, and a family of morphisms, which is dinatural in X. And this family, I'll denote it with an I instead of a D. And this universal property here can be given precisely as follows. So universal means in this case, that for every dinatural transformation D of source H, there exists a unique morphism F sub D from L to D that makes the following diagram into a commutative one. So another way of saying this is that there exists a category of dinatural transformations of source H. Morphisms in this category are given by morphisms of the category C between the underlying objects, which make these structural morphism diagrams into commuting diagrams. And now the coend is the initial object of this category. So for every dinatural transformation, there's a unique one, a unique morphism, which with target this dinatural transformation and with source the coend. Okay, so the idea to the idea for coends is simply that they are objects with structural morphisms that satisfy some important universal property. And now there is some existence result. This result is due to Majid and Lyubashenko. Majid proved all of this structure, and then Mashenko proved that, in fact, the Hopf algebra Majid constructed is the coend we talked about before. So here are some references. But anyway, the proposition is the following. So the assumptions here are just that C is a modular category. And it holds more in general. But anyway, so in our setting, we care about modular categories. So if C is a modular category, there exists a unique coend for that functor up to isomorphism. So it exists and it's unique. And furthermore, this coend has a very rich structure. So it has a braided Hopf algebra structure in C, meaning it admits morphisms which give a product, a unit, a coproduct, a co-unit, an antipode, and they all satisfy axioms for braided Hopf algebras. I won't recall them precisely right now. I will just show you some pictures that define these structural morphisms for the Hopf algebra L. And these morphisms are defined essentially using the universal property of L. So for instance, let's look at the co-product. So here on the right, you have a dinatural morphism in X, because the structure morphisms for the coend, these morphisms IX are dinatural. And if you compose with some morphism here, you can, by dinaturality, make it have it appear here with a dual. Then you can turn the dual, you can make the dual disappear by moving past the cup. Then you have another duality, dinatural morphism. So it comes up out here with a dual, and then you get a dinatural morphism. So since this is a dinatural morphism from X dual tensor X to L squared, then it will induce a unique morphism from the coend to L squared. And this, we call it the coproduct, right? And with this kind of universal property of the coend, you can define multiplication, product unit, coproduct, co-unit, antipode, this is the antipode. So this all follows just from the universal property. And now I will finish on this slide for today, I think. I will tell you what is the coend in the explicit example I introduced earlier. So this example of small quantum SL2 will be kind of a recurring example for all the structure for all the algebraic ingredients I will introduce. So if you take C to be the category of representations, of finite dimensional representations for UQ bar SL2, then L is realized by a special object called the coadjoint representation. You can see Lyubashenko's paper for the proof. And this object is given as a vector space. So this is the category of representation. So as a vector space, this is just the linear dual of UQ bar SL2, which is a finite dimensional vector space. And the coadjoint UQSL2 action is defined as follows. So X acting on a linear form F is defined using precomposition of F with something that's defined in terms of the antipode and the coproduct. So this is a Sweedler's notation for the coproduct, and you can kind of inverse conjugate an element of the quantum group using X and evaluate F against it. This will give you the evaluation of coad XF on this element. Right, so this is for the object underlying the coend, and you have a family of dinatural morphisms that's defined as follows. It's very natural. So if you have a representation for the quantum group and you consider a linear form on this representation, an element of the dual representation and an element of X, then you obtain a linear form on the quantum group just by evaluating every element of the quantum group by acting on small x and then evaluating with the vector in the dual of big X, of capital X. So anyway, this is kind of the very explicit example of the coend in the main. So for quantum SL2, and I think probably this is a good place to stop for today. And tomorrow I will finish introducing the rest of the algebraic setup I need, and I will tell you how to use it to construct three-manifold invariants.
Great, thanks, Marco. Are there any questions?
I had a quick question on the last slide.
Yes.
So let's see. The coadjoint action of UQSL2, what is it acting on? I didn't quite get
Oh,
that.
sorry. So F here is an element of the linear dual of the quantum group. So it's just a linear form on the quantum group.
Yeah.
And you can define a structure of a representation on this vector space for the quantum group itself.
I see.
So, yes, so you need to act on every linear form with an element of the quantum group, and the action is defined like this. So this is kind of a short notation, maybe a confusing one for a linear form.
Yeah, that makes sense. Thanks.
Okay.
I would have a question then. So in the construction with non-semisimple categories, how explicit are the, say, invariants of three manifolds? In semisimple case, for example, you exploit the fact that this coend that you just mentioned is very explicit.
Right. Yes. So in the semi-simple case, you can reformulate everything with just considering the list of simples which dominate the category, and then using Kirby colors as defined by Turaev. And here we have, so it's kind of, this is as explicit as Henning's invariants. So in fact, there is an algorithm for, in this setting at least. So in the general setting for general modular categories and general coends, I wouldn't say this is the most explicit approach, because in fact, everything is defined by exploiting this kind of universal property of the coend. So it kind of you know there exists a unique something that does something, but I think in the examples, for instance, for quantum SL2, then you need to identify every relevant piece of structure. So for SL2, this is very, very explicit. You just have some Henning's algorithm. Probably before Henning's, it was even like Lorentz universal invariant algorithm to just figure out the combinatorics of elements of the quantum group when you want to compute an invariant for close to for a link, for instance. And Henning's decided to use a certain linear form on the quantum group to extract a number. This is the integral. I will talk about this tomorrow. But the integral is explicit. So for SL2, everything is rather explicit. In general, I'm not so sure. And maybe I should also say that I'm giving an example using SL2 just because SL2 is very quick to define, but everything generalizes to all small quantum groups. So all Lie algebras, simple Lie algebras at least. Well, but then.
Other questions? Well, I have another basic one. So if you start with something like a ribbon category, okay. So my basic question is, if you have some algebraic input and you want to build a TQFT out of it, how do you decide which dimension of the cobordism you should consider? And to make this a bit more specific, if you start with a ribbon category, you're drawing these three-dimensional pictures for the morphisms, and they live in vector spaces. They live in these home spaces. So somehow my first instinct might be to associate vector spaces to three manifolds, but then you would be looking at something like maybe a 3+1 dimensional TQFT. So how does it boil down to 2+1 here?
So in fact, the way I will be using these diagrams for morphisms in order to construct something that's defined for surfaces and three manifolds, first thing you will construct, like in my plan, will be invariants for three manifolds. And in fact, you can present three manifolds by surgery. This is not the only approach. So you can also, there are constructions by Turaev and Vero, for instance, that use presentations of three manifolds by triangulations. But if you look at the surgery approach, then essentially a framed link determines a closed three manifold, and several links can determine the same manifold. You have some Kirby calculus on links that will tell you when different presentations actually determine the same three manifold. But anyway, the bottom line here is that you will look at links, and the link will be a three manifold or a framed link. And so this is how like a one-dimensional object in the three sphere actually is telling you about an invariant for closed three manifolds. And then the way this construct, so we will extend this invariant to a functor on cobordisms using a very general recipe that's called universal construction, that was introduced by Blanchet, Abeger, Masbaum, and Vogel. And the way this works is you start from an invariant for n plus one dimensional manifolds, and you extract from it a functor on the category whose objects are n dimensional, so one dimension less, n dimensional closed manifolds, and morphisms have dimension n plus one. So this is why, starting from surgery presentations, then we define a TQFT in dimension 2+1.
Cool, thanks. Are there any other questions? Not for now, it seems. Okay, then let's all thank Marco again.